Good evening, everyone. I hope I'm audible and my screen is also visible. And so, this is tutorial 11 of the NPTEL course Advanced Linear Algebra. So, like in other tutorial courses, in this tutorial also, I will discuss some problem which may help you to solve the assignment 11 of this current course. But there is a point which I left in the last tutorial, that is, I did not done any problem in the regarding adjoint, which are supposed to be done in the previous tutorial. So I will do one problem from there, and I will continue to do the problem for this week. I mean, this week, whatever is required in this week, whatever is there, that's regarding mainly normal operators, self-adjoint operators, and what others is there. That I think unitary operator and the ISO uh, preserving inner products. Those things is there. So So let's begin. So this is, I hope I'm audible. If there is any problem with my network, or there is any issue with my voice or anything, I mean, if my voice is not clear or my screen is not visible, you just you can write in the message text section, or you can open your mic and let me know so that I can try to fix them. Okay, so this is tutorial 11. And today is 4th April. So, okay, so what is adjoint of a operator? We have discussed what is the inner product space and all this. Even if you have any doubt regarding those or any old content which I already discussed, you can ask me here. I can try to explain them once again. Um, okay, so let's start. Let V be an inner product space over a field F. So that means an inner product space is nothing but the vector space with an inner product given on it. Uh, Inner product given on it. Inner product is something that must satisfy some linearity in the first component, anti-linearity in the second component, and it should satisfy the homogeneity, that norm of alpha, which is equals to norm of alpha square, which is equals to inner product of alpha comma alpha, is greater than equals to 0, unless alpha is 0. Okay. So let V be an inner product space, and let T from V to V be be an finite dimensional inner product space. Be a finite dimensional inner product space. Let P be a linear operator. Then the operator, then there exists basically, then there exists unique, there exists a unique linear operator T star from V to V, such that inner product of T alpha beta is equals to inner product of alpha T star beta, and this should hold for all every alpha beta belongs to the vector space, belong to the inner product space V. So then there exists for every linear operator T on a finite dimensional inner product space V, there always exists a linear operator T star, which is something different. Basically, you can say that there exists another linear operator A, which will satisfy this condition for every alpha beta in V, T alpha beta equals to alpha inner product T beta. But that A is called, if this satisfied by an operator A, then that A is called the adjoint of the linear operator T. And then T star is called the adjoint of the linear operator T. And how this happens, how there exists, I mean, there exists, here I'm saying there exists a unique linear operator that depends on a finite dimensional inner product space. If you have a linear functional, that linear functional has to be, if you have a linear functional on a finite dimensional inner product space V, then every linear functional must be look like this. So there must exist some beta such that f alpha is equals to inner product alpha beta. This is already, I think I have not discussed this, but I think this is discussed in class. So even if you have any, if you want to prove this, I can ask. I will try to prove that. But okay, otherwise I'm not going to that. I'm not going to be telling those things. So, so this is the existence of, I mean, there exists an adjoint of a linear operator. But the point here is that if here is another one remark you can say if B beta be an order basis of the inner product space V, then the matrix representation of TB T star beta, matrix representation of the linear operator T star. We have for a linear operator T, we have an adjoint linear operator T star, right? Now, if you obtain the matrix representation of the linear operator T, um, TBN linear operator and ABN matrix of the linear operator, then AKG is to this. And I think do I need to find out some space with linear operator in any orthonormal basis or let BN or not order basis. I need orthonormal basis. Orthonormal basis. So orthonormal basis is an order basis where each elements are in each elements are orthogonal to each other. Okay, elements are orthogonal to each other. Orthogonal basis, orthogonal basis for V such that PB, that will be TB. This is a matrix. Its adjoint. We know what is this is the transpose, conjugate transpose. This is for matrix A. A transpose is actually the conjugate transpose of A. That means you have to take the transpose and then, or you have to take the conjugate and take the transpose. This is what it is. And what is orthonormal basis? If you recall, the orthonormal basis is collection of vectors alpha 1 to alpha n such that each alpha I, alpha j inner product is actually equals to delta ij, that is equals to 1 if I not equals to I equals to j, and basically I can write this is equals to 1 if I equals to j and 0 if I not equals to j. This is what it is. That means norm of every vector is 1 and each vector is orthogonal to each other. Okay, and this fact is called alpha is orthogonal to alpha j. Okay, so now let me do one problem if possible. Okay, I think I have to write that problem. Okay, let me write this problem. So the problem is that, okay, no, right. Yeah, this is the problem. So what this problem says, if P from x, y, z is a linear operator look like this way, that x plus y plus z, z plus x is a linear operator on an inner product space R3. So here it is the over real field. Okay, here it is, we are not in the complex field. Here it is over real field. And this is the vectors inner product space equal to the standard inner product. And for V is equals to R3 over R, that is here V is the R3 and the field is R. The standard inner product is actually x1, y1, z1. This one with x2, y2, z2. These are the element in V. The standard inner product is equals to, this is what it called standard inner product. Standard inner product is actually, this is equals to summation, or we can directly write. You can write x1, x2 plus, here it is real, so there is no bar or conjugate will not be here. This is what is the standard inner product. And let T star denote the adjoint of the operator T, then we have to find T, 2, 3, 5. Okay. So, how to find that T star actually? So if I take any vector x, y, z, this one with, I want to obtain, suppose I want to obtain T star of this. So let me ask, what is T star of this? So T is given like that, T x, y, z is equals to x plus y, comma y plus z, comma z plus x. And here one point I must point out, that whenever an adjoint of a linear operator exists, that has to be unique. So there can't be two adjoint of a single linear operator. Okay, that adjoint has to be always unique. So if you have this, then I want to obtain what is T star x, y, z. Okay, I want to obtain, or you can alpha, beta, gamma. For alpha, beta, gamma, I want to obtain what is this. Okay, so now by the formula rules that x, y, z with T of T star of, I want to obtain this one, right? And this has to be equals to, this has to be equals to This has to be equals to inner product of T of x, y, z with alpha, beta, gamma. This has to be equals to like this. And this is equals to x plus y plus z, z plus x, comma, okay, T x plus y plus z. So there is another way you can do, I think. Okay, let me try this. If this does not work, then I'll do that. Then alpha, beta, gamma. Okay. So now this has to be equals to alpha x plus y, comma beta y plus z, comma gamma z plus x. This is for all x, y, z belongs to R, right? Now, this is what it is. Now, if I take and to obtain 2, 3, 4, 5, right? That one. So, if this is equals to if T star alpha beta gamma is equals to T star alpha beta gamma is equals to alpha prime beta prime gamma prime, then this side actually will be equals to, or this side will be equals to, that will be equals to alpha prime x plus beta prime y plus gamma prime z. Okay, so that means this is equals to alpha of x plus y plus beta of y plus z plus gamma of z plus x, and this is true for all x, y, z belongs to R. So in particular, if I take x is equals to 1, y is equals to 0, and z is equals to 0, then what I will get, that left hand, this one will become, so this is what it is. Suppose this is the star, this is star, so star should imply that x is equals to 1. If I take x equals to 1, so y equals to 0 and z equals to, that means alpha dash is equals to x is equals to 1, so there will be alpha plus beta y plus z, that is 0, gamma z plus x, and x is 1 and z is 0, so that's why gamma. And similarly, if we take x is equals to 0, y is equals to 1, and z is equals to 0, then what I'll get, if from here, from left hand side, I will get beta prime, which is equals to if I take, I have taken x equals to 0, z equals to 0, so y equals to 1. So this one will become alpha, and y equals to 1, z 0, so this one will be beta, and this one will become 0. So that this is what it is. And if I take x is equals to 0, y is equals to 0, and z is equals to 1, what I will get, that left hand side will be this gamma dash. Gamma dash is equals to x and y 0, so this term will disappear, and this term will be only beta will be there and gamma will be there. This is what it is. So what we obtained, that T star of alpha beta gamma, that is equals to alpha plus gamma, alpha plus beta, and beta plus gamma. This is what it is. I hope I'm correct. Okay, so now alpha plus gamma, alpha plus beta, alpha plus gamma, alpha plus x is 1, y is 0, z is 0. So alpha plus gamma, y is 1, alpha plus beta, z is 1, beta plus gamma. Yeah, this is correct. So this is what it is. So therefore, in particular, we have obtained complete full form. So, but I have asked to find 2, 3, 5. So 2, 3, 5. That will be first alpha plus gamma, that is 2 plus 5, comma alpha plus beta 2 plus 3, beta plus gamma, that 3 plus 5, that is equals to 7, 5, 8. Yeah, this is what it is. So correct answer is 7, 5, 8. This is what it is, and automatically all other will be discovered. So I hope this is clear, right? If there is any doubt, you can let me know. I will try to explain. Maybe I'm something using which is not trivial, then you can ask also there. Is that clear? So now, here is another problem. I have defined, okay, let me see what is there. It is linear product space, polynomials over the field, and equipped with the inner product. Equipped with the inner product, what is given, and it be the defined like this, which of the function is correct. Okay. So yeah. Okay. Yeah. It's okay. Thank you. So here is another problem that is based on the inner product. So let V be the inner product space of all polynomials over the field C. That means the space of all polynomials where the coefficients are coming from the complex number. This is what it is. I mean by this statement. equipped with the inner product. This is the inner product given, that inner product fg is equals to integration over 0 to 1 ft gt bar dt. So that means gt bar is applicable here, because here we are completely in, here we are um, yeah. So here complex thing is there. So let mf be the linear operator defined by this. Here mf is actually called the multiplication operator. That let's v to v. V is an inner product space right now. So mf on an element g is actually multiplied by f dot g. Here f dot g is a function, and that means a polynomial. That f dot g at the point x is actually fx gx. But when I write f compose g at the point x, that means f of g of x. So there is two difference. F dot g, f compose g. F dot g means that is multiplication, and f compose g means this is composition. Okay, this f of gx. This is what it is. Which of the following statement is incorrect? So question is, which of the following statement is incorrect? That we have to find. Okay. Okay. So first thing is that I think here it is. Here it is composition. Achha. Achha, this is correct. Okay, so here it is. Note that MF is an operator. This is an operator. This is a linear operator, right? Linear operator. I am not checking. This is linearity. All these things. That's there, but I am not checking this. The first question is that M of F1, F2. That at the point F, whether this is composition of two operator or not. When we write T1 is an operator and T2 is an operator, then T1 compose T2. This is what it is for two operator T1, T2 on the vector space V. Let me write what it is mean by the composition of operators. We have seen the product of two functions. We have seen the composition of two functions. They are element in the vector space V. But if T1 and T2 are two operator on the inner product space V, then T1 compose T2, or composition, just sometimes writing as the product, that at the point x, or at the vector alpha, is equal to T1 of T2x. This is what it is for all alpha, for all x belongs to the vector space V. So this is working like the composition function. So that's why this is composition. Okay, that's why this is not usual product. This is what it is usually. I mean, think as a composition operator. So this way, if I write mf1, mf2 at the point g, that by formula f1, f2, g. This is product. This is right now pointwise product. Now we can write that m of f1 for the function f of f2. That we can write m of f1 for the function m of f2 at the point g. So that means right now they are actually composition of these two operator, m of ff2 and at the point this operator at the point g. Okay. So this is what it is. So that is composition of two operators. So that's why this is as a statement correct option. So that means this is as a statement this is correct, but that's not the correct option, because correct option is I have to find the incorrect statement of among all of these. Okay, and the another is that m of f star is equals to mf. I think this will be the incorrect. So let me check what is m of f star here. M of f star, I have to find what is m of f star. M of f star at the point g, whatever it will be. Suppose for any two function g and h, for any two function g and h coming from the vector space V, m of f star g at h, that has to be equals to, by the formula, g at m of f h. Okay, that has to be equals to g of f dot h, and that by inner product rule 0 to 1 g of f, and I think gt, yeah, gt f of t h of t its bar dt. Right, now we can, I have to write like this way. That means I can write f f bar ft bar gt into ht bar integration over 0 1 dt. Then we can write this way. Then what I can say, that actually this is equals to f bar dot g with inner product h, because f bar dot g at the point t is equals to f of t bar and g of t. This is what it is by definition, where this is what it is, the function. So that means That means from here what I can say is that m of f star g is actually equals to f bar dot g. Okay, so that means, but here it is asked that, and that means this can be written as m of f bar at the point g, the multiplication by f bar, that's the this is the function. So that means m of f its adjoint is actually m of f bar, but here it is just said m of f, no bar is there. So that's why this option is incorrect option. So this is the correct, for our purpose, this is the correct answer. Okay, and the operator is normal, so that we can check what is mean by normal. An operator P from V to V on an inner product space V is normal if, sorry, not if, this is definition. An operator is normal if T star T is equals to T star. That means T should commute. This is called T should commute with its adjoint. That is T commutes with its adjoint. That is T commutes with its adjoint. Okay. So this is what it is mean by the normal. Okay. So the question is that here, third option is that MF normal. This statement is correct or not? MF is normal operator. Normal operator. Indeed, we have checked that mf star is actually the multiplication by m of f bar. That maybe that's not the correct option. I mean, there the option was mf star is equals to m of or not. This is what it is. But actually, mf star is actually m of f bar, right? Multiplication by f bar. Indeed, we observed that m of f star is equals to this one. Then m of also, and another thing is that, and m of f1 f2 is actually equals to m of f1 composition m of f2. That's the multiplication of two operators basically. Okay, this is what it is, the multiplication of two operators. Note that here it is multiplication of two function. Okay, and here it is multiplication of two operators. There, you should not be confused with these two terminology. Okay, so now these two fact is there. Now if I write m of f star m of f, then by first formula we can write m of f bar, and second formula m of, this is what it is. Now by second formula, this can be written as, this is composition right now. This is composition right now. So here T1, T2 means this is composition. When I write T1, T2 for two operator, that means that is composition. But already I have seen T1, T2 at the point X means T1 of T2X. But when I write F1, F2, that's not like this. F1, F2 means the multiplication. But F1 compose F2 means composition. Okay. So now we can write this one, and this is by the second formula. You can write that f bar dot f, because composition of two operator is actually multiplication by that, this type of things. And we know that for two function f and for any function f bar dot f is actually same with f bar, and that now again by the second formula mf, m of f bar, this is composition, and this is equals to mf compose m of f star by the first formula. So that says this mf is actually normal. So that means the third option as a statement, this is correct, but as a answer to this question, this is incorrect, because I have to find the incorrect options. And m of f bar star is m. That is once again that is correct, because we have obtained m of f bar star, that has to be equals to m of f bar bar, and that is equals to m of f. So that is also the correct statement. This is also the correct statement. So as an option, this is incorrect. So I hope this question is clear. If there is any doubt, anything, any confusion, you can let me know. I'll try to explain those things once again at least. Okay, so I'm going ahead for the next problem. Okay, thank you. So what this problem says, let V equals to C2. That's the two-dimensional complex field. This is be an inner product space over C and equipped with the standard inner product. So as it is standard inner product in complex, standard inner product I can write. So first point is that standard inner product in Cn is, suppose inner product of x1, x2, xn and y1, y2, yn. These are the two elements in Cn. Linear product is actually summation of xi, yi bar. Okay, but this also can be written if I consider this is as a column vector. If we consider this as x, y star. If I consider x is equals to the column vector, sorry, row vector. X is equals to something like that, x1, x2, xn. This is the row vector, yeah. Then this is what it is. You can do that way. Basically, my point is that you can write x, y star. Y star means considering y as a 1 by considering y as a 1 by n order matrix, then y star is actually adjoint and it's sorry conjugate and transpose, that is equals to y1 bar all the way yn bar, and now it is the matrix multiplication. This is what it is. Okay, but I'm not going to do anything with that. Maybe when I'll need, I'll go to that. Okay, so now the question is that consider the linear transformation T from C2 to C2 whose matrix representation with respect to standard order basis is ABCD. So matrix, so standard order basis is actually standard order basis standard order basis, and that is itself is an orthonormal basis of C2 is 1 comma 0. This is the ordering also 0 comma 1. Okay, and the matrix representation of, and let's take this is the matrix representation of TB is equals to AB CD. Okay, if T is equals to U1 plus T U2, where U1 U2 are self-adjoint operators on V, then matrix of U1 with respect to what is the matrix error. And here it is question that let T is equals to U1 plus U1 plus ITU. Okay, sorry, this is not T. U1 plus I is the complex conjugate square root, actually square root of minus 1. I, U2. Then question is what is U1 and where with where U1 and U2 are self-adjoint, yeah, linear operators on V. Self-adjoint linear operators on V. Then the matrix representation of U1 with respect to B. This is what it is. Then the matrix representation of U1 with respect to B. Okay. Now I'll come to the problem. But before that, there is a new terminology that is called self-adjoint. A bounded linear operator T on a finite dimensional inner product space is said to be self-adjoint if T star is equals to T. That means its adjoint is actually equals to the operator T itself. But the point here, if you try to note that when I'm writing adjoint term, I'm trying to involve, that time I'm always taking a finite dimensional linear product space. Because in finite dimensional linear product space, there is a guarantee that you will have the adjoint of a linear operator. But if you are not in finite dimensional linear product space, then there is no guarantee that for a bounded linear operator you will have an adjoint of, sorry, for a linear operator you will have an adjoint. A bounded linear operator you have, but bounded is separate thing. If you take an infinite dimensional linear product space and you are considering a linear operator on that, then there is, this is no bounded thing is not there. A linear operator T on a finite dimensional linear product space is said to be self-adjoint if this happens, because whenever we are considering linear operator, that linear operator may have the adjoint, may not have the adjoint. But if B is finite dimensional inner product space, in that case you will always have the adjoint operator. So that's why whenever we are trying to involve the adjoint, or that time we will always consider finite dimensional inner product space. Okay, so here it is finite dimensional, there is no harm to consider. But in fact, in infinite dimensional inner product space, still there is the many places there is the adjoint of a bounded linear operator actually. Okay, so now if you consider the linear operator T, then T can be written as T1 T plus T star T plus T star by 2 minus I times, sorry, T plus I times T star minus I times t minus it star okay. I can write a is equals to a plus a star by 2 minus a minus a star by 2 plus, then what it will be, here it is I, okay, is it I, let me check, yeah, this is correct, yeah. So no, this is t minus, no I is not needed here, this is correct. So I can write this as t plus t star by 2 plus t minus t star by 2. I can write, there is no problem because this is what it is. Just usually I have added t star, subtracted t star. This is what it is. But note that if a is equals to t plus t star by 2, then a star is equals to 1 by 2 t plus t star whole star, and that is equals to 1 by 2 t star plus t is equals to a. So that is a is self-adjoint. Here I must note that, or you can note that for two operator T1, T2 on a finite dimensional inner product space T1 plus T2, there is some property which I have not said that time. I forgot to say that T1 plus T1 star plus 2 T star. You can check, and T star its adjoint is again the linear operator T. I mean, if you do the adjoint two times, you'll get the T. This is basically representing something like conjugation of a complex number. If you take a complex number, take the conjugate of that, and you take the conjugate once again, you'll get the number once, get back your original number. And another property that T1 T2 star is actually T2 star T1 star. These are some property which I forgot to mention when I'm considering the adjoint. But here is, this operator is self adjoint. Here it is asked that u1 u2 has to be self adjoint operator, right? Now, but t minus t star, if I consider this is the operator, this is equals to b, then its star, actually what it will be, minus t star by 2 whole star. Okay, this is will be equals to 1 by 2 will be there outside, then by the formula t star minus t, but this is equals to minus t minus t star by 2. So that means it is equals to minus b star, it is becoming minus b star. Okay, so that is, this operator is actually this, that is b is not self adjoint. But if we just add here I and here 2i, I is the square root of unity, then if b prime is equals to I t minus t star by 2i, then we know that conjugate of I is actually minus I. That is we know. Then we know conjugate of I bar is actually minus I. So that means b dash its star is actually equals to t minus t star by 2i its adjoint, and 2 is constant, there will not be any problem, but this will be minus 2i, right? And here it is t star minus t, and that will be equals to t minus t star by 2i, that is equals to b dash. So that why b dash is actually is self adjoint. Then, so that is what I actually obtained, that that t operator t can be written as t plus t star by 2 plus I times t minus t star by 2y. Okay, this is the self adjoint as a sum of, as a, where these are self adjoint you can write. So u1 is actually equals to t plus t star by 2, and u2 actually equals to t minus t star by 2i. So we have asked to find what is u1 with respect to the standard order basis. With respect to standard order basis, that will be exactly equals to t plus t star with respect to the standard order basis. Okay, where beta is actually here I'm writing. B is the standard order basis. Recall that this is beta actually, not B. 1 0 0 1 is the standard order basis. Okay, so this is what it is. But we know that this is a linear operators and this standard order basis are going to be like very smoothly. So now, and we know that if we take a linear operator T and this is an orthonormal basis, which is also an orthonormal basis, then if you just first what I have said, if you I hope I have said that if you consider a linear operator, here it is. If you consider a linear operator T and consider its adjoint, that is T star, if you consider a beta be an orthonormal basis, then the matrix representation of T star with respect to that orthonormal basis is actually the matrix representation of T with respect to that orthonormal basis and its adjoint. Okay, so that means from here what we can say, 1 by 2, this will be outside, T beta plus it will be like matrix representation of T and its adjoint. Here it is means the matrix and its adjoint. Here it is means the adjoint of the operator and its matrix representation. Okay. When I am writing T star inside the bracket, that means we are considering the operator T star and trying to find its matrix representation with respect to the basis beta. And when I am writing this one, that T beta star, that means that we have the matrix T beta, matrix of T with respect to the order basis beta and its adjoint. Adjoint of a matrix, as I have said, this is conjugate transpose. Okay, this is what it is. Now we have ABCD. T beta is actually equals to ABCD. This was given. Then this will be equals to 1 by 2 ABCD and transpose of this operator matrix, conjugate transpose. That is A bar, B bar, C bar, D bar. So that can be written as 1 by 2 A plus A bar, A plus A bar, B plus C bar, C plus B bar, and D plus D bar. That is actually equals to real part of A, because we know that real part of, I think if I trying to get the exactly what it is in the options, yeah, these are the options. Real part of B, and this will be like B plus C bar by 2 and B bar plus C by 2. This is what it is. So here as real part of an complex number z is actually equals to z plus z bar by 2. Okay, so that means this is actually u1, and if similarly you can obtain what is u2. So similarly obtain u2 with respect to the matrix representation b2, sorry, with respect to the matrix representation beta. Okay, so which option is correct? So let me check the options. This is the option, that real part of A plus B plus C bar by 2, B bar plus C by 2, and real part of B. This is the correct options, and these are, you can check, this is not correct option. These are all not correct option. You can check. There, these two are not correct clearly. Here you can check. We first in this place it has to be B plus C bar by 2 bar. Here it is written B bar plus C by 2. So that means that has been taken as a transpose once again, but that's not the correct. Okay. So is it clear? Okay. So if you have any doubt, you can let me know. I'll try to explain that once again. Even that may be very trivial, still that is not a problem. So it's okay. Let me go to the next problem. So what this problem says, let V be the P3R, that means the space of all polynomials of degree at most 3, and that is a 4-dimensional space. And W equals to R4, that is what is called, that is usually 4-dimensional inner product space, and that over the field real R. Now the inner product on V and W are given by this way. Inner product on V is given by this way, and inner product on R is given by this is real, so that's why this inner product is actually look like this. So there is no bar. There will be no bar actually at all because this is real. So that bar will not make sense here. Okay. Then which of the following, statement is or are incorrect? Dimension of V not equal to dimension of which of the following is or are correct? Dimension of V is not equal to dimension of W. First of all, note that is what I have said first. Dimension of V is actually equals to 4. Three-dimensional spaces of all polynomials, spaces of polynomial functions of degree at most 3. In that case, in fact, we know 1 x square x cube is an order basis of V, but that need not be orthonormal basis. Okay, that I will go to why this need not be orthonormal basis. In fact, this is not an orthonormal basis. Yeah, this is not an orthonormal basis. But note that this is not an orthonormal basis. Note that this is not an orthonormal basis. So what was orthonormal basis? Maybe not needed here. Just I'm trying to remind you. What is orthonormal basis? Orthonormal basis has to be an order basis with only additional fact that alpha I, alpha j inner product that has to be equals to 1 if I equals to j and 0 if I not equals to j. This is what it is, orthonormal basis. Okay. This is what it is. Okay, let me just go. Okay. Then which of the following? The first option is incorrect. So there isn't 4-dimensional. There has to be 4-dimensional. Dimension of V is 4-dimensional, and W is equals to R4 over R. That is 4-dimensional. The first option is incorrect. There is no confusion. So that's maybe very straightforward. Okay. There exists no isomorphism map from V to W. There will always exist an isomorphism map. If we have two finite-dimensional, there is a statement I can mention. If V and W, so that's theorem you can say. Maybe I'm not mentioning completely. Let V and W are two finite-dimensional inner product space over the same field F, then if V and W are two finite-dimensional inner product space over the same field F, then dimension of what is isomorphism, that I need to mention. So I have to mention isomorphism. So I'll mention inside this. Then dimension of V is equals to dimension of W if and only, this is what it is called, if and only, sometimes it is if and only if there is an isomorphism from V onto W. So what is isomorphism? What is isomorphism? I hope you all know, but still I just want to recall what is isomorphism. Note that isomorphism is something about a linear operator T from V to W is called isomorphism if T is 1 1 and onto, that is bijective, and the most important property that T alpha T beta is equals to inner product alpha beta. So note that here alpha beta is on V and this is on W for all alpha beta coming from the vector space V, inner product space V. So okay, here I just want to point out one trick or one standard rule of the mathematics. Whenever you have some algebraic structure, these are called algebraic structure. When you have group, whenever you have field, whenever you have a vector space, whenever you have an inner product space, there is something algebraic structure. There is some rules that's maintaining that those things. Now, whenever you have a vector space, in that case, if we consider vector space means they are sometimes called linear space, right? Vector space are sometimes called linear space. Whenever you are giving a map from one vector space to another vector space, what was the basic necessity of that map? is that map has to be linear. That means that map has to be satisfy the property that C alpha plus beta is equals to C of T alpha plus T beta. This is what it is. So why this is the basic necessity? Because V is a linear space, there is a linear structure. If you take any vector alpha and beta and a constant C, if you take any vector alpha, beta in V and constant C coming from the vector space V, then C coming from the field C, then C alpha plus beta that has to be on the vector space V. Okay, whatever I am trying to say right now, that's not in our syllabus or anything, but that's something standard in mathematics. That's what I'm trying to say. So whenever you trying to read or study some map from a map from an inner product on a vector space, there the basic necessity is that map has to be linear. Okay, but whenever you give an inner product space structure actually an vector space with an inner product, then what will be the standard requirement for a map? That standard requirement is that map has to be a well behaved map. Basically an well behaved map from these two space is something that has to be satisfying this type of property. Okay, that inner product preserving. Suppose you have a group, for example, if you have a group and you are giving a map from a group to group, that's usually called group homomorphism. Then there should be some property that should satisfy. That property is that should maintain the group structure. Okay, and homomorphism, that if we take two element like alpha beta in the group, here it is not there, and then f of alpha beta has to be f alpha f beta. That's the usual group product. Okay, so these are the standard thing. Whenever you have an algebraic structure and you are considering a map, that map has to satisfy some type of very interesting property that aligned with the structure given on that. Now, whatever I have tried to say, if you are not able to understand that, forget about it. That's not a problem. Okay. So now, here it is the thing that isomorphism, whatever in vector space, what is the isomorphism? What is the usual bijective? What is the one-on correspondence means? That's the bijective linear operator. But whenever we give an inner product space structure on those spaces, then requirement is that there has to be bijective. But as we have an inner product, that inner product has to be preserved. This is called preserving inner product. Okay. Now this is called the isomorphism. Okay, T is an isomorphism. This happens, whatever it is, right? T is an isomorphism if this happens. There is a bijective. I mean, V and W are said to be isomorphic to each other, and then V and W are said to be isomorphic to each other. Here, V, in that case, here in this case, V and W are said to be isomorphic to each other. But this is not our target. So this is something like definition. I'm saying what is I mean by the isomorphism here. But the theorem says that if V and W are two finite dimensional inner product space over the same field F, then dimension of V are two dimension of V equals to dimension of W if and only if there is an isomorphism from V and W, V onto W. How that happens? That T from V to W. Suppose we are considering V and W are two inner product space. Okay, finite dimensional and dimension is same. Suppose V has an orthonormal basis beta V and W has an orthonormal basis beta W, and we can always get that type of orthonormal basis. How I will always get an orthonormal basis? Suppose V and W are inner product space. Okay, suppose you are taking an order basis of the space V, then you can use the Gram-Smith orthogonalization process, and you got the orthogonal basis, and after orthogonal basis you do the normalization and you get the orthonormal basis. So you will always get an orthonormal basis in an inner product space. Okay, through the Gram-Smith orthogonalization process. Now, if you consider V and W are two inner product space, they are finite dimensional and the dimension is same. And let's take BV and BW are the two orthonormal bases of V and W respectively. Then just map. Suppose alpha 1, alpha 2, alpha n is the orthonormal basis here. Here the beta 1, beta 2, beta n is the orthonormal basis. Then the linear operator T, giving by T alpha 1 is equals to beta 1, T alpha is equals to beta, that will be the isomorphism for two finite dimensional space. Okay. I hope this is the way this theorem is proved, but I am not going to use that. I am not going to prove that. So therefore, there exists an isomorphism from V into W because their dimension is same. So that's why this is a correct option. Okay. Dimension of V equals to dimension of W, that is also correct option that we have checked. And there exists an isomorphism from V into W. Why all the options are correct? Am I doing a mistake? Oh, there is no isomorphism. Sorry. This statement I'm reading wrong. There exists no isomorphism. That's not correct. There exists an isomorphism from K to W. That's correct. There is no isomorphism. That's not correct. So this is the theorem which will give complete answer to these questions on how to prove this theorem. That you have to consider two orthonormal bases on from left hand side, from the right hand side, and you have to map sending the orthonormal bases one to other. This is what it is, and that map can be linearly extended to the full space, and we can prove that that map is actually um, yeah, that map will be bijective. That's very much clear because I am sending an orthonormal basis to another orthonormal basis. And why that map will respect this property? Because if you take alpha 1 all the way alpha n is the orthonormal basis of the space V, and beta 1 all the way beta n is the orthonormal basis corresponding to the space W, then T alpha 1, T alpha I, alpha j for any two vector, this has to be equals to, you can check, that has to be equals to, this is equals to by the rules that beta 1 beta I comma beta j, but beta I beta j is an orthonormal basis. That's why it will be delta ij, that is 1 if I equals to j and 0 if I not equals to j, and that is equals to alpha I alpha j. So basically what we obtained, T alpha I, where delta ij is equals to 1 if I not equals to j and 0 if I equals to j. Now this happens on the basis spaces. Now if you take any vector alpha belongs to V and write alpha is equals to summation of xi alpha I equals to 1 to n, and beta, and another vector is something like, suppose this is not alpha, suppose this is take two element like f and g, f and g, like f is equals to this one and g is equals to summation of yi alpha I equals to 1 to that, then you can get that fg inner product is equals to summation of over all ij xi yj bar, and inner product of alpha I alpha j, and you will get that this is summation of xi yj j, because alpha inner product alpha I alpha j is 1 if I equals to j and 0 if I not equals to j, then you will get that this is actually the standard inner product type of things, xi yi xi yi. This is single summation. Here it is double summation. So then you can check that TFTG, which is actually supposed to be equals to inner product T of summation of xi alpha I and T of summation of yj alpha j, and you will get that this is equals to inner product of summation of xi beta I, and this is summation of yj beta j, and similarly you will get the summation of xi yi bar. So that means inner product of fg equals to inner product of pftg. So that way it will hold. Okay, I hope it is clear. I am just doing the proof. I've done the proof here. Okay, is it clear this problem? If you have any doubt, you can let me know. I'll try to explain. Okay. Okay, so let's go into the next problem. So let T1, T2 be two self-adjoint operators on finite dimensional inner product space V. Okay, over the field C. So that means T1 star equals to, that is T1 star is equals to T1 and T2 star is equals to T2. This is self-adjoint operator. Let the power star denotes the adjoint. This is what it is. Already we are doing that of the corresponding operator. Then which of the following statement is or incorrect? AT plus BT2 is a self-adjoint wherever AB belongs to C. So let's check whether AT T1 plus BT2 it's adjoint. Let's check. By the rules, I know that AT1 star plus BT2 star, because that we have said that T1 plus T2 star is actually T1 star plus T2 star. You can easily check. That's very much easy. So now that is equals to, for any scalar, if you write CT star, that has to be equals to C bar is equals to, this is number one rules, this is number two rules, C bar T star. That is you can also check. So this will be equals to A bar T1 star plus B bar T2 star. So whether if a b belongs to complex number, then a bar t1 star plus b bar t2 star is not necessarily okay. Now we can write it at a1 plus t1 plus b bar t2 because t1 and t2 are self-adjoint. So that's why t1 star is equals to t1 and t2 star is equals to t2. But a and b are complex number. They are adjoint. Their conjugation is not necessarily equal. So this is not necessarily then suppose a t1 plus b t2 star is not necessarily equal to a t1 plus b t2. Okay, that's very much clear that, for example, if you take a is equals to I, then what is I bar? That is equals to minus I. And suppose b is equals to, suppose a is equals to I and b is equals to 0. So in that case, it will be like it and its star, its it1, its star is equals to minus I t1 star, which is equals to minus I t1. So it is not self-adjoint. Okay, this operator is not self-adjoint. This operator is not self-adjoint. Just for example, this is example. So from here, it is very much clear that when this will be self-adjoint. That's very much clear that, note that if a and b are real, note that if a and b are real numbers, then a t1 plus b t2 is self-adjoint. So this is what it is necessary condition, and this is this is sufficient condition, and this is necessary. This is necessary. You can look at necessary. So that means that we have to take that a b positive. Sorry, real number, not positive, real number. Then you will get. If a b real number, then you know that a bar is a again and b bar is b again. So that will be self-adjoint. Okay. So that option is not correct, first of all, because here it is said that AB is coming from the complex number. Second option is that T1 plus IT2 is normal if and only T1 T2 star plus T2 star T2 T1 star. This is something called double commutant, but okay, I'm not going to that. So here it is, question is asked to that T1 plus IT2, T1 plus IT2, T1 plus IT2. Check, we have to check that this is normal or not. Okay, this is A. Let A is equals to T1 plus IT2. We know that T1, T2 self-adjoint. We have the operator A equals to T1, T2. We have to check that this is normal or not. So let's A star plus A, which is A star A, that is equals to T1 plus I T2, its star adjoint, and that is T1 plus I T2 is equals to, this can be written as T1 star plus I bar, and I bar is minus I. So minus I T2 star whole into T1 plus IT2, but I am little confused. Here we have given that self-adjoint operator. So that means T2 star, this fact is same with T1, T2 equals to T2, T1, because T1, T2 is self-adjoint, right? Okay, so that means we can write it as T1 star T1, that is T1 square basically, plus I T1 star T2 minus I T2 star T1 minus I square. So that will be plus 1 T2 star T2. Okay. Now, and another way, on the other hand, we have to check what is the condition on T such that A is actually a self-adjoint operator, normal operator, under the standing assumption that T1, T2 self-adjoint. Okay. A star, this is equals to T1 plus IT2 into T1 plus IT2 its star. So that will be equals to T1 plus IT2, and once again this will be T1 star, that is self-adjoint. So okay, let me still write this way, T2 star, and you will get that T1 T2 T1 star, that is self-adjoint. So that's why it will hold minus I T1 T2 star plus I T2 T1 star minus I square, that is plus 1 into T2 T2 star, as T1 star is equals to T1, T2 star is equals to T2, then A star is equals to A star A. This will give, we can easily cancel out this term with this term. Okay, we can easily cancel out T2 star by T2 star, because this is actually T2 square, nothing else. And this term, this implies that, so this will give that I T1 T2, this is the first term, minus I T2 T1, that is equals to these two terms, that is minus I T1 T2 plus I T2 T1. So if I cancel out I, then what I will have, T1 T2 minus T2 T1, that is equals to minus T1 T2 plus T2 T1. So that will give that 2 times T1 T2 is equals to 2 times T2 T1. So if you cancel out 2, then we will have that T1 T2 is equals to T2 T1, and that's basically T1 T2 star, because that is self-adjoint. T2 star T1 or something, whatever it is given. So that option is correct, no doubt. Okay, T1 T2 star and T2 T1 star. If you do in general, I hope maybe you will get the something. Okay. Yeah. So this is what it is. We are done. So that means that T2 T1 star. I think this is what it is. So that means second option is correct. Okay. Now let's go to the third option. The set of all self-adjoint operators on V forms a group under the addition operator defined as this one. Okay. What is we mean by group? Whenever you have two elements, a group actually, I mean, to check the let V. I think V it is written, right? What is the let V? V be the set of, no, the set of all self-adjoint operators. So self-adjoint operators, I'll write let S be the set of all self-adjoint operators on the inner product space V. Okay. The question is whether this is forms a group or not. With the addition, define an addition on S by like this T1 T2. If I take two elements coming from the element S, they are self-adjoint already. Then T1 plus T2, this is a new element I want to define, that has to be equals to T1x plus T2x. So first question is whether this is, so if I take two elements, whether their addition is there or not. If you know that T1 T2 self-adjoint, then T1 plus T2 is self-adjoint. If it is clear, it is very much direct, you can say. Even if you still have doubt, you can ask, I'll try to explain. It is clear that T1 plus T2 is self-adjoint. That implies that T1 plus T2 is actually in S. Now, we know that identity operator is self-adjoint. So that to form a group, what I need to first consider that we have a binary operation, that binary operation is this is the addition. So with respect to addition, I have to check whether this is a group or not. So clearly zero operator is self-adjoint. Zero operator. So let me write zero operator which sends every element to the zero, that is a linear operator, right? Zero operator is a self-adjoint operator. So that is the additive identity in for S. To form a group, what I need to do, first we have to check whether it is closed under addition. Second, that is what it is, that if T1 T2 is there, T1 plus T2 has to be there. Second, I have to check whether additive identity is there or not, that's zero operator is there, and I have to check for every element there is a inverse. This is what is the last condition we need to let T belongs to S. Then minus T is again a self-adjoint operator. That says that T plus minus T is equals to 0, that is additive identity. That implies minus T is additive inverse of T. Okay. So that says that S is group with respect to addition. S is a group with respect to the addition defined above. Defined above means this is the addition. With respect to this addition, this is the additive group. Okay, so I don't know. I hope all of you know what is group, but I already said a group is something, a structure with an operation that has to be closed under that operation. There should exist an identity with respect to that operation, and there should exist inverse of every element with respect to that operation. This is what it is, group. Okay. So this is so T the set of all self-adjoint operators on V form a group under the addition operators defined by this. So this is correct option then. Okay. The composite operator is a self-adjoint operator. Composite self-adjoint operator. Okay, let me check. Let T1 compose T2. We know T1, T2, this is what it is composition. Its adjoint is equals to T2 star, T1 star. Now, if T1, T2 is self-adjoint, then this will be T1, T2, T1. But that is not necessarily equal to T1, T2, right? So that means T1, that is composition of two operator if in addition. This is what it is. In addition, if T1, T2 self-adjoint. The composition operator, that is composition operator, need not be self-adjoint. They need not be commute. This is what it is. We require that T1, T2 has to be T2, T1. That is means commute. If I take two operator, there is no guarantee that they will commute. In fact, how we'll get that things that if you okay, one second. If you take self-adjoint operators, then that will no, that need not be commute. That need not commute. For example, if you take if you take two matrices which are self-adjoint, okay, then they need not commute with the other matrix, right? Like like I can give you example. 1, 1, 1. This is self-adjoint, right? This matrix is self-adjoint, and let's take 2 and 3. This is also self-adjoint. This is T1. This is T2. Then let's check what is T1, T2. This is 2. This is 3. This is 2. This is 3. And what is T2, T1? This is 2. This is 2. This is 3. This is 3. This is very much clear that T1, T2 is not equals to T2, T1. They are all are self-adjoint. Note that T1, T2 is self-adjoint. In fact, more than one thing. This is real function, self-adjoint, right? So they are self-adjoint, but they are not commute. So whenever they not commute, the T1, T2 star need not be self-adjoint. Okay. So that means last option is incorrect. Is this question clear to you, all of you? If you have any doubt, even very simple, you can ask. I'll try to explain it more and once again. Is it clear to everyone, this solution to this problem? If you have any doubt, you can ask. Or even if I go ahead little bit for the next problem, you can still therefore at that point you can ask. I'll try to explain it. Go back and explain it again. Okay. I hope then it is clear. If it is still there is any doubt, you can let me know. I'll try to explain. Okay. I'm going to next problem. This is problem number. So this is what we done. Yeah. This is a problem. So let's see what this problem says. Let alpha 8. Sorry. Oh no, sorry. I think we have checked this. No, I have not checked this problem. Okay, this is different problem. Let T1, T2 be into self-adjoint operator on finite dimensional inner product space V over the field C, and let star denotes the power. Then which of the following statement is incorrect? So here it is asked which of the following statement is incorrect. So we have checked in the previous that we have already mentioned in the previous problem. In the previous problem, we have said that AT1 plus AT2 will be self-adjoint if and only if AB is always real. If it is not real, then then that will not be self-adjoint. That's very much clear. Okay. So that means this option is correct. So okay, here I have to find the incorrect option. So this option is correct. So that means as an answer, this is not a correct answer. Correct option to choose. Okay. I have to find the incorrect options from the previous problem. You can check. But because in the previous problem in the first problem I have said that AT1 plus BT2 will be self-adjoint. Under the standing assumption that T1, T2 self-adjoint, the condition needed is that A and B has to be real. I think that I have made remark or note. So even if you have doubt, you can ask me, then I'll try to explain once again. So from the previous problem. Okay, let me go there. I have mentioned that. Here it is. Note that if a and b are real numbers, then this is self-adjoint. Okay. So because a t1 plus b t2 is look like its adjoint is look like this way. Now if this t1 t2 self-adjoint, then we have this one. So this has to be equals to a t1 plus b t2. If we know that a equals to a bar, b equals to b bar. Okay. So from this problem, we can say that that this is self-adjoint. I mean, this is as a statement, this is correct, but as an option, this is not correct because you have to find the incorrect options. Next question is that T1 minus IT2 is normal. Did I done this option also somehow? No, this is minus it is. So okay, let me check this. So let's take A is equals to T1 minus IT2. Okay, this is self-adjoint. A star, A is normal if and only, I mean, then if A is normal, then, I mean, this is standard assumption. Just 1 second. Okay, so A is normal. That means what we know that then we can write A star is equals to A star A. That means T1 minus IT2 its adjoint, T1 minus IT2 its adjoint is equals to T1 minus IT2 its adjoint and T1 minus IT2. Okay. So now what we'll get that T1 minus IT2 and we know that its adjoint is actually T1 star, that is self-adjoint. Okay, let me still write this way. Okay. So T1 minus I bar T2 star, that is equal, that has to be equals to T1 star minus I bar T2 star, and that has to be, this is T1 minus IT2, and we know that I, this is equals to IT2 and this is self-adjoint, T1 is self-adjoint and I bar is minus I, that will be plus I T2, which is equals to T1 plus I T2, T1 minus I T2, and that has to be equals to T1 square. Basically this is self-adjoint, T1 square plus I T1 T2 minus I T2 T1 minus I square, that is will be plus 1 minus 1, so plus 1, it will be plus T2 square, that has to be equals to T1 square minus I T1 T2, that will be I T2 T1 minus I square, that will be plus T2. T2 square, T2 square cancel out, this is cancel out. So what will obtain? I will can cancel out, that will be like T1 T2 is equals to T2 T1. You can check that you have to take this term left hand side and you have to take this term to the right hand side, you'll get the, okay. So T1 T2, this is what it is, and that is same thing with saying that the option, what was the option, second option, that T1 T2 star equals to T2 T1. So that is same with saying that T1 T2 star is equals to T2 T1 star, because that is self-adjoint. I hope there is a little problem with the, I mean, no problem, but I think they missed by mistake written star, but there will not be any star. Okay, so that means basically in this case this is normal if in this case it is normal if T1 T1 and T2 are commutes. That commutes, that implies that T1 T2 is equals to T2 T1. We have done one problem similar like this. So this is as a statement, this is correct, but as a option this is incorrect. Okay. Okay. So let's go to the second problem. T1 plus T2 is normal if T1 star T2 star is equals to T1 T2. This is already there. We T is self-adjoint. In the previous problem, we have checked we have already checked that, we have checked that T1 plus IT2 is normal whenever T1 T2 is equals to T2 T1. This is what we have checked in the previous problem. If you go back, here it is. Yeah, here it is. That T1 T2 equals to T2 T1. That if we know that condition, that is a necessary condition. If we know that condition, you can go to the reverse direction. You get that A star equals to A star. And we know that A is, a T1, T2 self-adjoint operators, that we know. Okay. So that means, that says, then that will give the answer, because here it is the second, here it is questions, option 3 and option 4 asked about the normal property of T1 plus IT2, and that happens whenever T1 equals to T2, that we know. But this option is nothing. This option is just says that T1 T2 equals to T1 T2. That's not saying anything else. Okay, so but we need that fact T1 T2 has to be equals to T2 T1. In the previous counter example, here we have provided an example T1 and T2, where T1 and T2 not commutes, but they are self-adjoint operator. So as they are self-adjoint operator, you can check that T1 plus IT2, this is not normal. You can check this is not normal. You can check that. That's very much clear. That because if you know that this is T1 plus T2 has to be self-adjoint normal operator, then necessarily T1 T2 has to be equal to T2 T1 under the standing assumption that T1 T2 self-adjoint operators. Okay, so this is as a statement correct. This is as a statement correct, but as an option it's not the correct option, because you have to find the incorrect option. So this is as a statement incorrect, but it is a correct option. So correct option is this. Is this questions clear, or should I explain some points little more general, or little more once again? Okay, I hope it's clear. Even if you have any doubt, you can let me know. In fact, even I'm going to the next problem, and during that problem, you can let me know. I'll try to explain it once again. So I'm going to the next problem. So okay. So what this problem says, this next problem, this is something we have to start. We have to read some new things here. So, but still, let's read what this problem says, and after that, we will. Okay. Okay. So, which of the following properties is or are not satisfied by a self-adjoint operator T on a finite dimensional linear product space? Okay. We have to find which of the properties are not satisfied by the self-adjoint linear operator T. First of all, eigenvalues of T are real. That's is a correct statement. Eigenvalues of T are real. That's correct statement. That's not a correct option. We have to find those. I'll come back. Why these eigenvalues of T are real? That I'll come back. But okay, let me see. First fact is that if T is self-adjoint on a finite dimensional inner product space V, then all eigenvalues of T are real. Why that happens? Let T from V to V is finite dimensional, because this is finite dimensional is very much required. Without that, in a self-adjoint terms, without that also this fact will be true. Without that, this fact will be true. Finite dimensional is not necessary. Other fact may be little problem, but this fact can be true without finite dimensional fact. Okay, let T be a self-adjoint operator. Then T star is equals to T. Let C be an eigenvalue of T, and alpha not equals to 0 belongs to V, be the corresponding eigenvector. Because corresponding to every eigenvalue, there exists at least one non-zero vector, which is called eigenvector, corresponding eigenvector, that is T of alpha is equals to C alpha. Now I have to prove that C is actually complex number. Let C belongs to complex number. I have to prove that C is real. So we have to start with like this way. This is very standard and method that now we know the linearity of the inner product. We can write C alpha alpha. First will be just directly it will go, and we know C alpha is equals to T alpha alpha. Now using the self adjoint, we can write this way. Now T is self adjoint, so we can write T into T alpha again. But we know T alpha is actually C alpha. Now C is in the second place. Now using the conjugate linearity in the second place of the inner product, this is the property of inner product. This will be C bar inner product alpha alpha. So that means C into norm of alpha square is equals to C bar norm of alpha square. Now you can write C minus C bar whole into norm of alpha square is equals to 0. But here we have mentioned alpha is non-zero vector. As alpha is non-zero, then norm of alpha, which is actually inner product of alpha comma alpha, that has to be non-zero. That is also one of the basic property of the inner product space. Even if you ask me, I'll try to explain. I'll try to let you know what are the properties that first conjugation in the first variable. Sorry, linearity on the first variable, conjugate linearity on the second variable. Another property is that inner product of alpha alpha is equal not greater than 0. Another property is that inner product alpha alpha greater than 0 whenever alpha is not equal to 0. This is the property I'm using here, and and this is all. This is all. And another property is that C. Oh no, this is all. Okay. So now this is 0. So this product with this is 0, and alpha is norm alpha is not equal to 0. That implies that C minus C bar is equal to 0. That implies that C equals to C bar. So that C is real. So what we obtain that every eigenvalue of a self-adjoint linear operator is actually real. Okay. This is the first fact as a statement correct. So as an option it is not correct option, because you have to find those statements which are not satisfied by a self-adjoint operators. Okay. So what are the second options? Eigenvectors corresponding to different eigenvalues are orthogonal. That is also once again another second fact. Second fact, eigenvalues of distinct eigenvectors. Sorry, eigenvectors corresponding to distinct eigenvalues corresponding to distinct eigenvalue are orthogonal. This is also very much easy. Why this is easy? So let me check. Let lambda 1 and lambda 2 are two eigenvalue of T. T self-adjoint, you know, for a self-adjoint operator. Of course, for a self-adjoint operator. We are not outside the self-adjoint operator. Okay. So T star is equal to that we know. And let lambda 1 is not equal to lambda 2, and let alpha 1 and alpha 2 are alpha 1 is eigenvector corresponding to alpha 1 not equal to 0, be the eigenvector for lambda 1, and alpha 2 be the eigenvector for lambda 2. So, okay. So then what we can start with, let lambda 1, alpha 1, alpha 2. We have to prove that alpha and alpha 2 is 0. That is what it is. Orthogonal means. To prove alpha 1 inner product alpha 2 is equals to 0. So we can write again, once again, using the linearity of the inner product in the first component, we can write this. This will be like T of alpha 1. So we can write T of alpha 1 is equal to lambda 1 alpha 1, T of alpha 2 equals to lambda 2 alpha, because alpha 1 alpha 2 are eigenvector corresponding to the eigenvalue lambda and lambda 2. Okay. T alpha 1 alpha 2. Now here is the self-adjointness we will use here. T star alpha 2. T is self-adjoint, so we can write it as alpha 2, T alpha 2. Now alpha T alpha 2 is equal to lambda 2 alpha 2. Now that we can write is that lambda 2 bar in the conjugacy alpha 1 alpha 2, but here lambda 1 lambda 2 are real number. Okay. Lambda 1 bar is equal to lambda 1 and lambda 2 bar is equal to lambda 2. That real number we know, that we have proved in the last one. So this can be written as lambda 2 alpha 1 alpha 2. So we can write is that lambda 1 minus lambda 2 whole into inner product alpha 1 alpha 2, that is equal to 0. But lambda 1 and lambda 1 not equal to lambda 2. So this will force you that alpha 1 inner product alpha 2 is equal to 0. That is alpha 1 is orthogonal to alpha 2. Okay. So that means this is also the eigenvectors corresponding to different eigenvalues are orthogonal. This is as a statement correct, as an option not correct, because you have to find those options which are not correct. And T preserves the norm. Okay, T preserves the norm means T preserves the norm. So statement like T preserves the norm. So what is mean by this? That is norm of T alpha is equal to norm of alpha for all alpha belongs to the space V. Okay, this is what it is. But that need not be. That need not be. Why that need not be? But this need not be. But this need not be true for general self-adjoint operator. Self-adjoint operator. Indeed, let's take 2003. This is a self-adjoint operator. I mean, you can consider it a matrix, and the operator is something like multiplication by this matrix. The column vector C2. Basically, this is right now. Let's take this is then T from suppose C2 to C2. This is the vector space. This is the vector space given by P on vector x1, x2, something like that. X1, x2. This is going to be like 2003 x1, x2. This is self-adjoint. So then this is equals to like 2x1, 3x2. Okay. So now T is self-adjoint here. T is self-adjoint, but norm of T x1, x2 that is equals to 4x1 square. So this is in complex field. So this will be 4 of mod x1 square plus 9 of mod x2 square. This square root. This not necessarily equals to mod of x1 square plus mod of x2 square, right? Which is actually the norm of x1, x2. That not necessarily. You can choose x1 1, x2 0, then you can check. Suppose choose x1 is 1 and x2 is 0. That means right hand side is right now. If you choose x1 is equals to 1 and x2 is equals to 0, you can check that first one will be 2 and second one will be 1. So they are not equal. So that means norm preserving property is not there. What is mean by norm preserving? That means that norm of T alpha equals to norm of alpha. That should satisfy for all alpha. But when you have a non-preserving property, that is actually called unitary operator. For an operator which has a non-preserving property called the unitary operator or isomorphism or isomorphic, yeah, something like that. Okay. So that means this is as a statement false. So as an option, correct option then. Okay. Matrix representation of T over an orthonormal order basis is Hermitian. That is also correct. Why that is correct? That I have said as a statement correct, as option incorrect. So matrix representation of T upon T with respect to an orthonormal basis. I hope orthonormal basis is said. Yeah, orthonormal basis over an orthonormal basis. Normal basis is Hermitian. So what is Hermitian? What is Hermitian matrix? Hermitian matrix means that is what it is the self counterpart of self-adjoint in the terms of matrix, and sometimes it is called self-adjoint. Hermitian matrix. A matrix A is called Hermitian if A star is equals to A, where A star is actually conjugate transpose of A. Conjugate transpose of A. So that is A star, its ijth entry actually Aji bar, where A is equals to its ijth entry is actually Aij. So here is the A star, its ijth entry is actually Ji'th entry of A and its bar conjugation. This is what it is. Okay. Basically, suppose you have some matrix like alpha, beta, gamma, delta. Suppose your matrix, the conjugation is like alpha bar, beta bar, gamma bar, delta bar. This is the conjugation. And if you have the equality, then you say that Hermitian. And here is the interesting fact is that fact is true. Matrix representation over then this is true. And I want to point out this is true. Why this is true? Note that if A be the matrix representation of T with respect to the A, be the matrix representation of T with respect to the orthonormal basis basis, what is the orthonormal basis? That alpha 1 all the way alpha n of V, I mean whatever however it is defined, then its ij entry is actually inner product of T alpha j with alpha I. This is what it is, the inner product. I mean, this is what it is, Aij. Then to prove A star, A is Hermitian, if the matrix ij entry of the matrix Aij, then we can write this is like this. Yeah? Its ij entry is actually Aij denoting by this, and this is exactly T alpha j alpha I. Okay. Now to prove, you can check this one. Okay, that is not very difficult. To prove, even if you still have doubt, you can ask me. I'll try to check why this happens. To just to prove, what you have to prove, that A is self-adjoint. Sorry, A is Hermitian. So to prove A is Hermitian, we need to show that Aij, that is the ij entry of this is equals to A star its ij entry, and that is equals to Aji bar for all I and j from 1 to n. Now how will show that? We have Aij is equals to inner product of T alpha j alpha I. That is equals to alpha j, comma, okay, let me write it clearly, T alpha j, comma, alpha I. That is equals to inner product of alpha j, comma, T alpha I, T star, but T is self-adjoint. So then I can use alpha j, comma, T alpha I, right? And there is another property of the inner product, that is T alpha I, comma, alpha j, that bar, that is T alpha comma beta, or any inner product. This is the general inner property of the inner product, that alpha inner product beta is equals to beta inner product alpha its bar. So this is what it is I am using. And T alpha I alpha j, this is what it is actually, the entry Aji and its bar. So that is what it is I want to prove, right? Aji bar. So that is A is Hermitian. So that is the A is Hermitian. That is the last property, is actually correct statement. As a statement, this is correct. So as an option, this is not correct. So is it clear? If you have any doubt, you can let me know. I'll try to explain it more. So what we obtain actually for a self-adjoint operator? First is that all the eigenvalues has to be real. Second is that the eigenvectors corresponding to distinct eigenvalue, that has to be orthogonal. Third, we have proved that the matrix representation of that operator with respect to any orthonormal basis has to be Hermitian or self-adjoint. I mean, Hermitian is the counterpart of the self-adjoint, but it need not be non-preserving. Okay, let's go to the another problem. Okay. So what this problem says, let A equals to, this is the matrix given, be an invertible matrix. Then there exists an unique lower triangular matrix M such that the entries on the main diagonal of M are positive, and M is equals to U is unitary, and the matrix M is like okay, whatever it is. I have to do it. Okay, so there is a theorem. Actually, there is a theorem that I have to mention. Okay, so that theorem says, just a minute. Achha, what is unitary operator? Unitary operator under a matrix. A matrix is to be unitary. An operator P or unitary actually denoted by U, from on a finite dimensional linear product space, V is said to be unitary if U star U is equals to identity matrix, identity operator, this one. And for the matrix, we will be saying like same way. That is called the, and where star is actually the conjugate transpose of the matrix. Okay. So now, what is the statement here? It is I wanted to point it out. That will be useful here. But statement is not much useful, but process is needed. So what does the statement says? Statement says for an, this is theorem, but there is a process to do that I'm going to discuss. Um, this is theorem, right? For every invertible matrix, square matrix, obviously invertible I'm writing means square matrix, invertible matrix uh, B, there exist a unique lower triangular matrix matrix M with positive diagonal entries on the main diagonal such that MB, that has to be U, a unitary matrix. So what it says, suppose you have a invertible matrix, you will always find a lower triangular matrix. That means the matrix whose elements above the main diagonal has to be 0. Something like that. Lower triangular matrix means this is, there can be non-zero entry, but they are all will be 0. This is the lower triangular matrix. There will always exist a unique lower triangular matrix. I am not going to use unique and all these things. Lower triangular matrix M with positive entries on the main diagonal, such that if you multiply that matrix from the left hand side, then you will get an unitary matrix. Okay. Of course, that, I mean, you have to, there exists always such matrix. That is what it is. Okay. So how that actually goes? So this basically goes uses the standard Gram-Schmidt orthogonalization process. So let's do it for the three matrix, and I will use that technique here. Okay. Okay. So we know that, I mean, how to do that. Basically, if we consider, let's consider full matrix, not a problem. Let um, B is equals to B and n by n invertible matrix. That means if B is equals to B1 all the way, B beta, I'm writing beta n, where beta i's are ith row of B. Suppose you have a B matrix, we consider each row. First row is the first beta 1, second row is the beta 2, and that way you get all the rows. Okay. These are the row actually. Okay, row of the matrix B. And this is an invertible n by n invertible matrix. Then this beta 1 all the way beta n, they are actually element in Cn basically right now, even in Fn. This is an linearly independent set. Why this is linearly independent? Because this is invertible. If it is linearly dependent, then that determinant has to be 0. Okay, this is very things which I have discussed very early. And if you have considered a matrix, if rows are linearly independent to each other, then you will get determinant is non-zero, and that is if and only. Okay, linearly independent. So then, by Gram-Schmidt orthogonalization process, Gram-Schmidt orthogonalization process, one can get an orthogonal basis that is alpha 1 all the way alpha n, where for this alpha i's or alpha k, that is what was the alpha k? Just I'm using the Gram-Schmidt orthogonalization process. I'm just recalling the Gram-Schmidt orthogonalization process. What is that? Beta k minus summation of beta k with alpha I inner product with alpha I square alpha I equals to 1 to k minus 1. This is what it is. Okay. Now this is the Gram-Schmidt orthogonalization process, and one gets what it is called that this is the this alpha k, this way the Gram-Schmidt orthogonalization process works, and one gets the orthogonal basis. Okay, alpha and alpha to alpha n. Now note that here, if you consider this alpha is actually okay. Now this alpha 1 by norm of alpha 1, alpha 1 by norm of alpha 1, note that these alpha I all are row vectors. Okay, they all are row vectors, 1 by n row vectors. Okay, all beta I alpha I all are row vectors, right? This alpha 1 by 1, alpha 2 by norm of alpha 2, all the way alpha n by norm of alpha n. If we do this, this is an orthonormal basis. Normal basis. Now here is one fact. These are all row vectors. Each of them are row vectors. Okay. Now one fact I am using here, a matrix, n by n matrix, U is unitary. That is U star U is equals to identity is equals to U star. If and only if its rows forms an orthonormal basis of the field Fn, row vectors. If you consider the row vectors of n entries, then unitary matrix, that will be unitary matrix if and only if it is an orthonormal basis. So therefore, as this is an orthonormal basis of the field Fn, that is basically either Cn or Rn, then alpha 1 by norm of alpha 1, considering it is first row, alpha n by norm of alpha n, this is, if you consider this, is an unitary matrix. Unitary matrix. On the other hand, B is equals to, on the other hand, B is equals to beta 1 all the way, beta n. Now, let's connect these things. We have for all k, we have beta k minus inner product minus summation of I equals to 1 to k minus 1 inner product of beta k with alpha I by norm of alpha I square with alpha I. Okay. Now if I divide it by alpha k, norm of alpha k, that will be alpha k, and this will be like I can divide alpha k here. Just a minute. Alpha k, this is alpha I. Okay, so we can think like this way. So okay, let me write this one. So that means I'll write next line I'll write. So this will be saying that alpha k is equals to beta k minus summation of I equals to 1 to n minus n. This can be written as cky. Yeah, cky and alpha I, where ck comma I is actually equals to inner product of beta k with alpha I by norm of alpha I square. So now if I divide it by with norm of alpha k, so okay, this is what it is. And then what I'll get actually, yeah, this is correct. Then we can write, this is my main point, we can write this vector, this is unitary matrix actually, some in between will be alpha k, that is what it will be alpha k by norm of alpha k square, alpha k not square, this is all the way alpha n by norm of alpha n. This matrix, each of them are row vector actually. This can be written as beta k, beta 1 that this can be written like this matrix. Suppose the first entry is of the k is equals to 1, so this will be like beta 1 all the way beta n, and the entries will be minus yeah minus okay, the first entry it is, so this will be like 1 by norm of alpha 1 0 0 0. Second one will be minus c, k is equals to 2 right now, 1 by norm of alpha 2, and this will be 1 by norm of alpha 2 0 0 0. And in this way the kth row will be minus ck1 by norm of alpha k square. I'll write this a little later. So in this way, okay, let me write this one once again. So this will be minus c21 by norm of alpha 2 1 by norm of alpha 2 and all the way 0. Next time is 0. So in this way the kth row will be minus ck1 by norm of alpha k minus ck2 by norm of alpha k all the way. Just kth entry will be minus ck1, that will be 1 by kk, 1 by norm of alpha k. Next is 0 0 0, and in this way we will get in lower triangular matrix. And if you just like trying to match these things, that k, this row, if you multiply this row with this column, so what will get? That beta 1 minus beta 1 into ck1 by norm of alpha k1. Okay, yeah, this is correct. Next will be minus beta 2 ck2 by norm of alpha k. Yeah, so this way it will match. This way it will match. So you get. So this is the process. Okay. So let me do this problem right now. So let me. In our case, this is the we have to do this problem. So I think this is completely will match. Okay. Let me do this problem. So here the matrix is given that. Here the matrix is given that. Okay. The matrix. Matrix is given that 1 by square root of t, 1 by square root of 2 0 0 1 0 0 0 1. So let's take here alpha 1. So here it is actually beta 1 is equals to 1 by square root of t, 1 by square root of 2 and 0. This is, and beta 2 is equals to 0 1 0 and beta 3 is equals to 0 0 1. So Gram-Schmidt orthogonalization process if you do, then alpha 1 is equals to, it will be as it is, and alpha 2 that has to be equals to beta 2 minus inner product with alpha 1 with beta 2 with alpha 1 by norm of alpha 1 square with alpha 1. So that will be equals to beta 2 is equals to 0 1 0. Now inner product of beta 2, that is this one, with alpha 1, that is same with, that is 1 by square root of 2, 1 by square root of 2 by norm of alpha 1 square. Here norm of alpha 1 square is actually equals to 1 by 2 plus 1 by 2, that is equals to 1. 1 into alpha 1, that is alpha 1 is actually equals to 1 by square root of 2, 1 by square root of 2 into 0. So this will be like 0 minus 1 by square root of 2, that will be minus 1 by 2 first, and second is 1 minus 1 by 2, that will be 1 by 2 comma, third will be like 0 minus 0, that is 0. This is what it is, right? Okay, and alpha 3, that will be alpha 3 is equals to beta 3 minus beta 2 with alpha, sorry, beta 3 with alpha 1 inner product by norm of alpha 1 square with alpha 1 minus beta 3 with alpha 2 by norm of alpha 2 square with alpha 2. So note that here is the interesting fact is that beta t orthogonal to both of the vectors. Sorry, beta 2 is actually orthogonal to, but beta 3, sorry, beta 3 is orthogonal to both alpha 1, because beta 3 last entry is 1, all other first two entries are 0, and here the first last entry is 0, alpha 1 alpha 2. So beta 3 alpha 1 equals to 0, that is once again same with beta 3 alpha 2. So therefore what we obtained here, it is exactly beta 3, that is equal to 0 0 1. So this is the orthogonal vector right now. So we get the orthogonal vector. Now we have to obtain the ortho normal. So how one will get the orthonormal? Here alpha 1 is equals to 1, that we know. That alpha 1 is equals to 1, and alpha 2, that is norm of alpha 2 square, that is equals to 1 by 4 plus 1 by 4 square. This is equals to 1 by 8, that is equals to, so alpha 2 norm of alpha 2 is equals to 1 by 2 square root of 2. I am correct? No, so this is 1 by 2. This is equals to 1 by 4, that is 1 by 2. So norm of alpha 2 is actually equals to 1 by square root of 2. Okay, but I don't need. But main point is that here, if we go that way, that formula, if I write, that formula says that the matrix M has to be, I mean, in the above formula, the matrix M has to be, there is not much place. So let me go a little down. Just a minute. Okay. So it's actually alpha 1. So here is actually the matrix M. Its ij the entry is actually, or kj the entry can be written like, kj can be written as minus 1 by norm of alpha k c kj, where if j less than equals to j less than strictly less than k, and is equals to 1 by norm of alpha k if j is equals to k, and another is the 0 if j greater than k. So if I do this process, so here what will get, beta 3 is equals to this, so alpha 3 is equals to this. This is what we got, alpha 3. Now if you do this process, you will get that that same process. If I just follow, then what I'll get, that we have the matrix 1 by square root of 2, 1 by square root of 2, 0 0 1 0 0 0 1. So the matrix that M will come here, that will be like 1 0 0. Next one is that minus x2 by x1, that will be, those calculations you have to do. I think you have to properly check that minus x2 by x1, that will be minus 1, this will be square root of 2, that is 0 0 0 1. So let me check whether this is doing the job or not. Yeah, let me check. The first one will be like, if we multiply, this one is unitary or not. So this matrix is actually equals to 1 by square root of 2. This will be like 1 by square root of 2. This will be like 0. This will be minus 1 by square root of 2. This will be minus 1 by square root of 2 plus square root of 2. Okay, accept, one second. This one is minus 1 by square root of 2, and this one will be 1 by square root of 2. This one. Okay. Okay, so this will be minus, this one is this will be minus 1 by square root of 2 plus square root of 2. Let's keep this right now. Yeah, let's keep this, and this will be like 0. Next term will be like 0 0 1. So now this can be written as 1 by square root of 2, 1 by square root of 2, 0, minus 1 by square root of 2. This will be like 1 by minus 1 by square root of 2 plus root 2, that is equals to minus 1 plus 2 by square root of 2, that is equals to 1 by root 2. Yeah, 1 by root 2, that is 0 0 0 1. This is clearly unitary matrix. This is a unitary matrix, you can check. Unitary matrix, you can check. So there, in fact, there is a general formula, I think discussed in class also, that if you have a matrix like x1, x2, 0, 0, 1, 0, 0, 0, 1, then then and with the addition that x1 square plus x2 square is equals to 1, and then the unitary matrix, that is actually x1, x2, 0, minus x2, x1, 0, 0, 0, 1, that is equals to, if this is b, then u has to be equals to this, and unitary matrix is the lower triangular matrix is 1, 0, 0, minus x2 by x1, and 1 by x1, 0, 0, 0, 1, with the whatever is given like x1, x2, 0, 0, 1, 0, 0, 0, 1. This is the standard one, and with the standing assumption that x1 has to be not equal to 0. Okay, so the question was the matrix M. We have to find the matrix M. Matrix M means this is the matrix M. This is the matrix M. So in our case, the matrix M is actually this is that 1, 0, 0, minus 1, root 2, 0, 0, 0, 1. This is the option, correct options, and all other options will automatically discarded. Okay. Yeah. So okay, I'll quickly do one more problem. So very quickly, I'll try to do one more problem. That if it is going to very fast, then I will do. Okay, so what it says that if this is the problem, what it says, if T is a linear operator on a finite dimensional linear product space V, such that the eigenvectors of T form an orthogonal basis of V, then T is necessarily self-adjoint. Okay, so if eigenvectors of T forms an orthogonal basis of T, if eigenvectors of T form an orthogonal basis for V, then T is diagonalizable, right? This is the first factor, and we know the matrix P, and if P be the matrix obtained by, if we consider P be the matrix, okay, I mean basically, and if P is equals to, and if P is equals to something like V1, V2, Vn, where V1, V2, Vn are eigenvectors, forms and basis, vectors of T which forms and basis, this form for which forms and basis, then matrix representation of T with respect to this basis, and suppose beta is equals to, and B is equals to this, say V1, V2, Vn. Okay, then matrix representation of T with respect to B is actually P, I think I'm correct, P inverse. Okay, this is a diagonal matrix. P inverse this with P is a diagonal matrix with diagonal entries, with eigenvalues as their diagonal entries. The eigenvalues as their diagonal entries. This is coming from very much from the standard thing that whenever it is diagonalizable, that diagonalization process, this is follow. Okay, but as here V1, V2, Vn is orthonormal basis, because this is not only eigenvector set, this is orthonormal eigenvector set, then P is unitary. Then P inverse actually P star. Okay, so my point is that whether this matrix is, so therefore if this is equals to suppose diagonal, so this if P inverse TBP is equals to the diagonal matrix like alpha 1, all the, not alpha 1, lambda 1, let's take diagonal, this is, let's take diagonal lambda 1 all the way lambda n. This is the diagonal matrix which diagonal entries are lambda 1, lambda 2, lambda n, lambda n. Okay, these are the eigenvalues. Okay, these are the eigenvalues of t with repetition. Then this will turns out to be p star pb. P is equals to diagonal lambda and lambda n. Now what are the questions that can be easily solved? T is necessarily, so that means we have a unitary matrix P star T with respect to the basis B. P is equals to diagonal lambda and lambda to lambda n. P is unitary. T is necessarily a normal operator. You can check. I think T is unitary. Unitary will not happen, but normal operator will happen. Diagonalizable is, of course, this is I mean I have to find. T is not diagonalizable. T is diagonalizable because we have the basis consisting eigenvectors. That's very much from the standard that T is diagonalizable. So this is not a correct option. T is necessarily unitary. That is an incorrect option. T necessarily self-adjoint. That is also incorrect. T is necessarily normal operator. That for sure, because then TB is actually equals to P into this diagonal matrix with with P star. Now you can check that TB star TB is actually equals to TB star. And why T is not necessarily self-adjoint? For example, if you consider the matrix A is equals to like uh, like 1 plus 2i 0 0 2 plus 3i, then A star is not equals to A, but A is diagonalizable because A itself is diagonalizable, but A is diagonalizable. That is, it has an orthonormal basis consisting eigenvectors. Okay, so I hope what I'm trying to do a little quickly, that T may not be diagonalizable. That is false, because we have because very standard thing that diagonalizable if and only if it has a basis consisting eigenvectors. But here we have an eigenvectors with, in addition, that orthogonal basis. They have orthogonal basis. Okay. Another thing is that so that's why T is diagonalizable. So this statement is false, and T is necessarily unitary. That is also false, because you can take this counter example. This is diagonal. This is the diagonalizable, and here we have whatever we required that we have, but this here it is not an unitary. Also, A is not unitary. So this will discard whatever we required here. T necessarily unitary, that option will be discarded. T is necessarily self-adjoint, that is option is discarded there. And T necessarily normal operator, that can be obtained from here, just to check this properly. Okay. So, okay, I hope this question is clear. Is there any doubt about these questions? Or anything till now, whatever I have tried to explain you, or anything you already had done in your course? Okay, if you have a doubt, you can ask. Otherwise, I will stop in few seconds. Is it clear then? Okay. So, thank you everyone. So this is the 11th tutorial. We'll meet in the next Saturday, in the same time, 6 to 8 p.m. Thank you everyone. So, yeah. So, if you have any doubt, you can ask me directly in the mail ID and directly in the class. Thank you everyone. I'm closing the tutorial session for right now.